Hello and welcome back everyone to Programming Horizons. I'm Deepika and today I'm going to talk about one of the most important topics in programming, data structures. Whether you are learning a programming language, building some software or preparing for coding interviews, understanding data structures is absolutely crucial. So today we will explore what are data structures, why do we need them, their different types, and we will also see some real life examples so that you can relate to them easily. Let's get started. So first of all, let us understand what is a data structure. As you can see, the term data structure is made up of two words, data plus structure. Data means raw facts and figures. For example, here we have a few names and numbers. This is data. Data simply means any information that we want to store, use or process. Now, if I arrange this data in the form of a table and assign column names, then this table becomes our data structure. So, data structure means how something is arranged or organized. And this brings us to a proper definition of a data structure, which says that data structure is a way of storing and organizing data so that we can use it efficiently. So why do we need data structures? Well, the first obvious reason is that it helps to store data efficiently. This in turn helps us to manage data easily, just like keeping things in proper shelves. It also makes code easier to manage and scale, since the program is able to handle more data in future if a good data structure is used. Using data structures also help us access and modify data quickly. If we want to find, insert or delete something, a good data structure lets us do that much faster than if it was just random data. And finally, by choosing the right data structure, we can save memory and processing time, making our programs faster and more optimized. Now let's take a look at different types of data structures that you will commonly use. We can roughly divide them into three broad categories, including linear data structures, non-linear data structures, and hash-based data structures. So first we have linear data structures where data is arranged one after the other in a sequence. Examples include arrays, linked lists, stacks, and queues. Let us understand them all. First linear data structure is array. An array stores items of same data type in a continuous block of memory. You can easily access items or elements by their index. Like to get the first item, we need to write the name of the array, which is ARR in this case, and then pass the index of the first item, which is 0, and that is how we get value 10. Similarly, you can access the other elements. Operations on arrays may include insertion, deletion, traversal, which means iterating through an array, updating, searching, and sorting. I have already covered arrays in C++ on this channel, so you can check that video if you want to see arrays in action. Next is list. In Python, we have already seen built-in lists, which are flexible containers to hold multiple values, similar to a shopping list. You can easily add, remove, or modify items in a list. Lists, tuples, sets, and dictionaries have already been covered in a separate video on this channel. Coming to the applications of arrays and lists, first of all, we can use them to store list of marks or scores in games. We can also use to store items just like in case of a shopping list. 2D arrays can be used to record data in row and column format. We have already covered this in C++ matrix videos. Another important linear data structure is a linked list. Unlike arrays, these are great for situations where you are managing a collection of items that might change in size. A linked list is like a chain consisting of nodes, where each node is divided into two parts. The first part is for storing the data, and second part is used to store the address of the next node in the list. In a linked list, each item points to the next, forming a chain. As you can see, we store the address of the first node under start pointer, and after that all the nodes follow, and the last node contains a null pointer marked by X or cross indicating the end of the list. A variation of a single linked list is a double linked list where every node contains two pointers to move both in forward and backward directions. Operations that we can perform on a linked list may include insertion of a node, deletion of a node, traversal through the list, updating a node, and searching a node. Since linked list allows to easily insert or delete items without shifting the rest, they are used in applications like music or video playlists, image viewers, and browser history navigation. Then we have stacks, which work on the LIFO principle. LIFO stands for last in, first out. Imagine that you have a stack of plates at a wedding hall. Here, the last plate that you placed is the first you will pick up. That means both the insertion and the deletion operations are always performed at the top of the stack. In the same way, we manage a stack inside computer's memory. Here we are making an array behave like a stack, and we are always going to perform insertion operation from the top. So the first element 10 is inserted at index 0. After that we insert 20 on top of 10, then 30 on top of 20, and so on. So the insertion operation will be performed from bottom to top, and this is known as push operation. That means the new element is always placed at the top of the stack. And now, since the stacks follow LIFO principle, so the last inserted item will be the first one to be removed. This is known as pop operation, and we keep on popping the elements until the stack becomes empty. Typical applications of stacks include back and forward buttons in a web browser, undo or redo mechanisms in text editors or image editing software since they follow LIFO principle, and recursive function calls. Next is the queue data structure, which is similar to a real-life queue. Imagine that people are standing in a line waiting for a bus. Whenever a new person comes in, he stands at the back or at the end of the line. And the first person in the line is the first one to leave the line. This approach is known as FIFO or first in first out principle. The same approach is followed inside queue data structure. We insert a new item at the back or the rear of the queue, and an item can only be removed from the front of the queue. This operation is known as dequeue. In computers, queues are used in CPU scheduling, disk scheduling, managing printer jobs, and handling requests on a web server. Note that stacks and queues are considered as abstract data types or ADTs. That's because they define how data is organized and what operations we can perform on them. For example, push and pop operations on a stack and enqueue and dequeue operations on a queue. But they do not define how to implement these operations. Usually, we use arrays or linked lists to implement them. If you want to learn how to implement stacks and queues in Python, then don't forget to check out my video on this channel. Now let's move on to nonlinear data structures where data is not stored in a straight line but is organized in a hierarchy or a network. Examples include trees and graphs. Let's explore them. A tree data structure looks like an upside down tree with a root at the top and branches below. Here in the diagram we are constructing a tree data structure. As you can see, there is only one single node at the top. This is known as the root of the tree. This root has two children on the left and right. These are known as internal nodes. These internal nodes have further children, and those four nodes at the bottom are known as leaf nodes. Leaf nodes are the nodes which do not have any children. These blue arrows between nodes are known as edges, and a branch is considered as any path from root node to leaf node. Operations on a tree data structure include insertion of a node, deletion of a node, traversal through the tree, and searching. Tree data structures are great for representing the hierarchical structure of an organization. Decision making, for example, while you are answering yes/no questions, and also for representing file and folder structure on a computer. For example, in this diagram, we have a main folder at the top which consists of three subfolders, and then we have a document folder which further has 3 files. So in this way we can represent the file or folder structure on our computer system using a tree data structure. Next is the graph data structure, which is another nonlinear data structure. It is extremely useful for representing any form of network. For example, in this diagram I have shown how 5 different computers marked as A, B, C, D and E are connected to each other in the form of a network. So here these red lines are known as edges. They show the connection between any two computers. On the other hand, these circles, which I am referring to as computers, are nodes. So therefore, we can say that a graph is a set of nodes and edges. Operations on graphs may include traversal, finding connected nodes, and also finding the shortest path between any two nodes. The real-world applications of graphs may include representing social networks such as on LinkedIn. In navigation systems, graphs can be used for finding shortest paths and also for representing computer networks. Finally, we have hash-based data structures which store data as key value pairs. For example, hash tables or dictionaries in Python. They allow super-fast lookups by key, like a contact book where you search for a name to get the phone number. Typical operations include insertion, deletion, or looking up values by key. So that's a wrap on my video on Introduction to Data Structures. Today we learnt about what are data structures, why do we need them, and what are various types of data structures. You can think of these data structures like storage containers where each is designed for specific kinds of information and for performing specific tasks. Using the right data structure helps us in performing operations like searching, sorting, and updating efficiently. Choosing the right data structure is super important because different problems need different types of data structures. And it depends upon factors such as what is the type of data being stored, what type of operations are required to be performed on that data, and what are memory and time constraints for processing. This is something that every programmer needs to master. If you enjoyed this video, then don't forget to give it a thumbs up, share it with your friends, and let me know in the comments which data structure you want to explore next. Thanks for watching, and I will see you in my next video.